Hello everyone, we are members of the IMFFT Research Institute, and in this video we would like to present an animated summary of our paper. We will cover the study test case, the numerical investigations, and then we will see how morphing wings can increase the aerodynamic performance of aircraft by manipulating the wake dynamics. So let's begin. In the context of the SMS project, the aerodynamic performance of an A320 wing was investigated both experimentally and numerically to evaluate novel electroactive morphing concepts aiming at improving wing efficiency. The A320 wing investigated here corresponds to a reduced scale prototype characterized by a 70 cm chord and a 60 cm span. It was analyzed for an angle of attack of 10 degrees in the low subsonic regime with a Reynolds number of 1 million, representative of a typical landing phase. Before going any further, we will introduce the computational setup whose intention is to replicate the experiments undertaken at the IMFFT. The computational domain consists in a rectangular prism with the display dimensions. The most upstream and downstream phases of the domain have been chosen as inlet and outlet boundary conditions. The top and the bottom walls are modeled with slip conditions. And finally, the lateral walls are modeled as symmetry walls. The Navier-Stokes equations are resolved numerically by discretizing the computational domain into a large number of cells, creating a multi-block grid. Now we can observe a 2D slice of this grid, which is homogeneous in the span direction. The total number of elements is approximately 300,000 elements for the 2D simulations and 10 million elements for the 3D simulations. Before introducing any design modification, it is essential to understand the reference flow physics. At these conditions, two recirculation regions are present. The first is a laminar separation bubble near the leading edge, and the second is another stable bubble near the trailing edge region. Both are driven by adverse pressure gradient conditions. Let's talk about the present wake dynamics. The presence of the wing creates a wake downstream of the trailing edge. This wake is delimited by two thin interfacial shear layers. The lower shear layer, which is formed underneath the wing on the pressure side, and the upper shear layer, which is formed on the upper side of the wing, the suction side. Both shear layers are governed by the shedding of co-rotating Kelvin-Helmholtz vortices. Due to the relatively high angle of attack and the supercritical shape of this wing profile, the effective shear on the lower shear layer is significantly higher than in the upper shear layer. This explains the formation of clearer and stronger Kelvin-Helmholtz patterns highlighted in dark orange in the bottom part of the wake in comparison with the one that we can see in the upper part pictured as green vortices. When the flow separates from both sides of the wing, the two free shear layers do not grow up independently. They interact nonlinearly through the pressure field they mutually induce, causing them to feed each other alternately. As a vortex grows on one side, it draws the opposite shear layer across the wake, breaking the Kelvin-Helmholtz mode and triggering the growth of the next vortex on the opposite side. This nonlinear feedback loop locks into a self-sustained alternating shedding pattern, which leads to the formation of Von-Kármán vortices farther downstream in the wake. Each of these coherent modes are characterized by their natural frequencies, whose identification will be shown later on via PSD analysis. Now it is time to introduce what morphing is. Historically, the wing was born as a flexible element able to adapt to the different flight stages at moderate speeds. But in practice, the wing became stiffer as the operational velocities increased. Nowadays, thanks to modern scientific developments, the rise in CPU power, new materials and artificial intelligence, it is possible to reconsider morphing and bring flexible concepts back. In our department, we refer as morphing to the technology which makes the wing able to deform and vibrate in an optimal way based on real-time adaptations. Morphing concepts are being developed for future aircraft configurations, targeting improved aerodynamics, green air vehicles, and efficient air transport. The type of morphing that we are working in our research group targets the manipulation of the wake dynamics, the promotion of the circulation around the wing, and the improvement of the SBLI dynamics. And all this is achieved by taking advantage of the feedback effects. A bio-inspired active trailing edge technology was developed to reproduce the dynamic behavior of bird feathers. The primary objective is to modify the wake turbulence by injecting kinetic energy at prescribed frequencies and amplitudes, in order to enhance the overall aerodynamic performance of the wing. The trailing edge motion is mathematically described by a quadratic displacement function, and the fluid-structure interaction is modeled using the arbitrary Lagrangian-Eulerian method, also known as ALE. This study focuses on the effects of actuation frequency, and therefore the remaining two parameters, morphing length and actuation amplitude, are kept constant throughout the simulations. The natural frequencies of the dominant flow instabilities were identified through PSD analysis of the pressure fluctuations measured at key locations. First, the analysis of pressure fluctuations at monitor point 1 in the region close to the wing highlights a low frequency mode around 8 to 12 Hz, which is related to the oscillations of the small laminar separation bubble located at the leading edge. Then, a dominant mode corresponding to the large bump of maximal spectral amplitude is observed and is related to the oscillation of the trailing edge recirculation region. This mode corresponds actually to the Von-Kármán vortex shedding between 130 and 140 Hz and is one of the major instabilities governing the far wake dynamics. Since we are dealing with low subsonic speeds, perturbations from far downstream in the wake are able to travel upstream thanks to feedback effects. Therefore, the recirculation region is typically known to oscillate at the Von-Kármán natural frequency. Two additional modes linked to Kelvin-Helmholtz instabilities dominate the near wake region, as shown in Figure B through the pressure fluctuations recorded at monitors 2, 3, and 4. These modes correspond to the upper and lower shear layer, with frequencies around 180 to 190 Hz and 205 to 215 Hz respectively. This difference makes physical sense. As mentioned earlier, the effective shear is stronger in the lower part of the wake, which causes the Kelvin-Helmholtz vortices to form faster there and therefore at higher frequencies. Finally, a sharp peak appears in the polar spectrum around 370 to 375 Hz, along with its harmonics at higher frequencies. This peak, close to the first harmonic of the upper shear layer, corresponds to the interaction mode between the two shear layers, resulting from the nonlinear coupling. Interestingly, and drawing from the chaotic dynamical system theory, despite this nonlinear interaction, the resulting frequency can actually be expressed as a simple linear combination of the natural frequencies of the upper and lower shear layers. These natural frequencies act as the key parameter for optimal wake structure manipulation. How close the vibration frequency is to each of them determines if lift increases, drag decreases, or both. This provides insight into the degree to which wake instabilities are altered and the role they play in the new flow scenario. This graph summarizes the aerodynamic response of the wing across the full range of constant actuation frequencies tested, from 10 Hz up to 600 Hz. The first thing to notice is a sharp peak in the mean lift around 210 Hz. This corresponds to actuation near the lower shear layer natural frequency, where an increase of up to 8% in lift coefficient is obtained. Around 185 Hz, close to the upper shear layer natural frequency, we observe a more moderate and smoother response in lift, reflecting the weaker reactivity of this mode to the morphing actuation when compared to the lower shear layer. On the other hand, actuating near the Von-Kármán frequency, 135 Hz, produces a strong response in both mean and fluctuating lift. This reveals how receptive this mode is to morphing excitation. The wave becomes strongly destabilized, with large force fluctuations reflecting the locking between the actuation and the dominant vortex shedding rhythm. Looking at the RMS curves, it is worth noting that the most beneficial actuation frequencies also tend to reduce force fluctuation, pointing towards a more stable and quieter aerodynamic response. The key takeaway is that the choice of actuation frequency is critical. Small deviations from the optimal range can either amplify harmful instabilities or unveil significant aerodynamic gains. The parametric study presented so far require a large number of high-fidelity numerical simulations, each corresponding to a single constant actuation frequency together with one actuation amplitude, one Reynolds number, and one angle of attack, making the full exploration of the parameter space extremely demanding in terms of computational time and resources. To overcome this limitation, an approach called Wobulation was explored, consisting of a linear sweep of the actuation frequency over time. The key idea is that a single simulation sweeps continuously through a wide range of actuation frequencies, allowing the identification of optimal frequency ranges in one single computation and drastically reducing the computational cost. As we can see in the graph, and it is fully explained in the paper, the aerodynamic force signals obtained through Wobulation closely mirror those obtained from the full set of constant actuation frequency cases, once a scaling law relating both approaches is established. Going back to the wave dynamics, we will talk now about the effects of constant actuation frequencies. Actuating at the Von-Kármán natural frequency strongly enhances the alternating vortex shedding, producing a significantly wider wake when compared to the static case, which results in an increase of drag. The local circulation is increased, but the wave destabilization is severe, with large amplitude force fluctuations. Actuating near the upper shear layer natural frequency produces a more subtle but beneficial reorganization of the wake. The interaction between the two shear layers is ultimately manipulated, delaying the appearance of the Von-Kármán mode further downstream while shortening the Kelvin-Helmholtz formation length. Actuating near the lower shear layer natural frequency strongly reinforces the lower shear layer vortices, dramatically increasing the local circulation around the airfoil. This produces the highest mean lift increase of all the cases investigated, around 8%, reflecting the high receptivity of this mode to the morphing excitation. Actuating close to the shear layer interaction mode, which is close to the first harmonics of the upper shear layer, continues to produce beneficial effects. The wake dynamics are reorganized similarly to the upper shear layer case, confirming that the harmonics of the shear layer natural frequencies are also effective targets for the actuation. Finally, actuating at the second harmonic of the upper shear layer natural frequency produces the most stable dynamic response of all cases, with the lowest increase of RMS compared to the static case. The wake structures are significantly attenuated, pointing towards a quieter and more stable aerodynamic system. We now present some preliminary results from the three-dimensional simulations to complement and extend the findings from the 2D parametric study. The overall trends observed in the 2D simulations are confirmed in 3D. Actuation near the shear layer natural frequencies produces beneficial reorganizations of the wake structures and aerodynamic performance improvements. A particularly striking finding from the 3D simulations is the progressive bidimensionalization of the flow induced by the morphing. In the reference case, without any kind of actuation, secondary span-wise instabilities develop naturally along the wingspan, adding a strongly three-dimensional character to the wake. Acting at 215 Hz, which is approximately the lower shear layer natural frequency, a noticeable reduction of these span-wise instabilities is already observed. The coherent structures become more organized and quasi-two-dimensional, suggesting that the morphing is effectively suppressing the secondary instability. This effect is even more pronounced at 372 Hz for the shear layer interaction mode, where the flow exhibits a strongly bidimensional character, with the span-wise coherent structures nearly completely suppressed. The results presented in this video provide a glimpse into the rich and complex aerodynamic phenomena that electroactive morphing can trigger, from the manipulation of shear layer instabilities and Von-Kármán shedding to the bidimensionalization of the flow and the efficient detection of optimal actuation frequencies through wobulation. All these findings are thoroughly detailed and physically analyzed in the paper, including the full parametric studies, the mathematical derivations of the scanning law, the time frequency analysis, and experimental and numerical validations, so we will only invite you to read for a deeper understanding. Finally, we hope this work opens new perspectives into the use of smart morphing concepts for future aircraft design towards more efficient, quieter, and greener aviation. Any questions or comments are welcome. Please do not hesitate to contact us, and thank you for watching.